Hi guys, in this video I'm gonna walk you through the realization of a worn out VHS post-process effect. It is the sum of many elements, more or less individually simple, that combined together will create a nice look, useful for some gameplay features. Said components can even become useful functions for the creation of totally different effects, if used in other contexts. For this project, you can follow the link in the description to download it. First things first, let's display the scene. When you're working with a post-process material, your scene has already been rendered. At this stage, you're basically treating it like a single texture that is going to be displayed at full screen. So, we first need to sample said texture containing the scene to be able to see it. To do that, we use the scene texture node set to post-process input 0. Remember that the output of this node is a vector 4, so let's mask out the alpha channel. Notice that in this node is available an input pin for the UV coordinates. In this case though, those coordinates are not coming from some mesh UV mapping, but contain each viewport pixel position divided by the viewport width and height. By noticing that, we can understand that all the image distortion operation will be placed before this node, while all the color manipulation ones will be done after. The chromatic aberration happens when different lengths of light radiation gets refracted by a lens at slightly different angles. That results in an offset of reds and blues in the image that creates some colored halo around the objects. In this case, it isn't very accurate calling the effect we are about to build in this way, but I think, given the visual result, it gets the idea. To build this effect, we need to sample the scene 2 times. Then, we need to multiply one scene for one of the colors we want our aberration to be. The other one for its complementary. And add them back together at the end. As you can see, the result is identical to the image we started with, and it needs to be like that. Since now we are going to offset the two scenes in different directions to create the halos, by coloring them with two complementary colors, it is assured that the scene will not get some weird tinting. Now, to finally get the effect we are looking for, we need to assign each scene 2 little horizontal offsets in opposite directions. To control exactly how many pixels this offset will be, we can get the reciprocal of the viewport width. The result of this operation is the amount to add or subtract from the hue of the UVs needed to move the image by exactly 1 pixel on the left or on the right. In other words, it is the pixel width in UV space. Let's use it by adding this value to one of the scene UVs and its inverse to the other one, once made it a vector 2. As you can hopefully see, we now have a very thin halo wherever there's a drastic chromatic change in the scene. To control of how many pixels this aberration is, just multiply the pixel width by the number of pixels wanted. Since in real life this effect is not sharp, we can give the impression of some blurriness by offsetting only one row of pixels every 2. To do that, we need to create a mask that's black on one row, white on the next, and so on. We can achieve this by calculating each row index by multiplying the v of the UVs by the viewport height and taking only the integer part of the result. After that, we can do the module of this number by 2, so that each row with an odd index number will be white, and each one with an even index will be black. Multiply the mask by the offset intensity and it's done. When played on modern screens, a VHS video is normally slightly blurred. This is because at that time the resolution was lower and the videos were interlaced. Even though the aim of this whole process is somehow to reduce the quality of the image in a certain way, we should still want our game to be playable when it applied. So now we're going to add a very subtle horizontal blur. It can be achieved in a very cheap way, by taking the pixel horizontal derivative, halving it and adding it to the image. Doing that in this dirty way creates some little artifacts around the object too, useful for this particular application. To simulate a bit the feeling of watching the scene through an old cathode ray screen, we can recycle some of the nodes we already added. We can duplicate the nodes of the aberration mask and layer the scene with it, turning the intensity as we like. As you may have noticed, a lot of the effects we're applying here are made in rows. This makes sense visually because of the way the data was encoded on tape and displayed on old screens. One thing that today we can immediately notice while playing an old tape is that the tones are a bit off. There isn't much contrast and the colors lack a bit of saturation. This is especially true in a worn-out tape. For this reason, we're about to intervene on the scene colors to simulate that look. To modify the contrast curve of the image, we can interpolate the scene with the square of itself and tune the alpha. This operation is a relatively accurate simplification of raising the scene colors to the power of a number between 1 and 2. But it uses less than half of the GPU clock cycles, so it's much more performant. In this specific case, with an alpha equal to 0.35, I'm simulating the elevation to the power of 1.25. After that, let's reduce the image contrast by raising the blacks and lowering the whites. To achieve a decent signal degradation effect, it is always needed the addition of some random noise. In this case, we'll add that as a very subtle effect, but it will definitely help us to create the sensation of looking at an old image that is upscaled from its original format. In fact, our noise will not have a different random value per pixel, but it will for rectangular pixel blocks. To do that, we need to calculate the 2D index of every pixel. We can duplicate the nodes for the horizontal intermittence and cancel the component mask nodes. Now we can divide these indices by 4 and 2, so that the integer part will be equal for blocks of pixels of that size. Append another scalar to make a vector tree and plug everything in a vector noise node. As you can see, we now have a grid of randomly colored rectangles. This is fine for a still image, but for what we need, this effect should be animated. To do that, we just need to append as third coordinate the time node, multiplied by the desired noise refresh rate. The refresh rate can be set to simulate specific video formats, 24 for cinema, 25 for European, 30 for American. Finally, we can apply this noise to our scene by lerping them and setting the intensity value. Let's keep going on with the signal degradation effects. We can add another one that was more specific of some types of these tapes. Let's generate a random value for each group of pixels row by copy-pasting the nodes from the horizontal intermittence. Divide that number by 4 and append a 0 before it and a frame rate after, then use it as coordinates for a vector noise node. Now we're going to use two channels of this noise for different purposes. Let's take the first UV channel and divide it by one noise channel. By doing that, we made each pixel row tile a random number of times. Notice that we had to clamp the low values of the noise to avoid divisions by 0, that would result in computation errors. Then, let's grab another noise channel and use it as a random offset for that same UV channel, by adding it to the division result. Now we can use these randomly displaced and scale UV values to generate some sinusoids that will be remapped in 0-1 range. We finally have our raw degradation mask that will be used to apply another pair of complementary colors. To apply the effect to our final image, we can lerp the two and tune the intensity of the effect. It is finally time to add some distortion to our image. The flagging is the partial horizontal shift of the image in all tapes that makes the images wave like a flag. As I said initially, every effect here should be made in a way that doesn't annoy the player, reducing the title playability. Since this effect is by definition very annoying, it will be placed in the upper edge of the screen, where it can still be perceived but doesn't come in the way. The effect itself is quite straightforward. Generate a gradient that is whiter where the image needs to be flagged, remap the values with an interesting function, and apply it as a horizontal offset to the screen UVs. For this specific case, I'll start from the screen G component of the VUEs, scale it up, clamp, and invert it. Now, to give it a curve that I like, I'll use the square tangent of these values. Now, you can multiply this result by some intensity value, append to it a 0 and add it to the screen UVs. To make this effect a bit more alive, we can vary its intensity randomly over time. Since I want said intensity to smoothly go from one intensity value to the next one, I'll have to interpolate two vector noise values per frame. So, let's start by taking our effect frame rate, appending it to a vector 2, and using the result for a vector noise. Now, let's do the same again, but let's grab the noise value that corresponds to the next frame. Now, I have one vector noise outputting the current frame random intensity, and the other one outputting the next frame one. I can interpolate the two by using the fractional part of the frame time. Notice how now the random value is not jumping from one value to another, but is smoothly transitioning. Now we can remap the range of this noise and connect everything to what we did before. This last component we're about to add is both an image color alteration and a deformation. So, after generating it, we'll apply it on both sides of the scene sampling nodes. The first part is identical to the color degradation. We have to obtain some random colored rows, but this time a bit thinner. For this time, we just need a grayscale value. Parallelly, we need to generate a gradient to evidentiate the effect affected area. Let's place these effects on the bottom of the image and a bit on top of the area affected by the flagging. Now let's combine it with the noise, so that the random lines will have a chance to pop only where the mask is not zero. This data will serve us to create the noise we're looking for, by acting as a variation for the input of a new vector noise node. Let's scale it by some factor and the pixel to the index, append to it our refresh rate, and plug everything in a new vector noise node. We now have a denser noise where the degradation intensity line is wider. Now we can mask out the rows that should have a zero intensity. Now let's slurp it in by using the degradation intensity as alpha, after giving it a proper remapping to have a better looking curve. Now it's time to do our last effort and create an UV offset from this effect, so that in correspondence of this noise the image will also be shifted a bit on the side. It can be quickly done by grabbing the intensity of degradation, scaling it, making it a vector 2 and adding the result as the UV offset right after the flagging. This was a long one, but apart from making this specific post-process, it gave you a bunch of useful examples on how the vector noise node can be used to procedurally generate useful data. Let me know what you think and which other post-process experiments you would like to see, and they will be discussed in future videos.